Hi everyone. Here we're going to continue talking about the sun, our star, my favorite star. We will be talking about sunspots and the cycling of sunspots, how they move, why the sun's magnetic field gets messy, what that means, and we will also talk about what are solar flares. So we cannot see inside of the sun. No light escapes. The photosphere is very, very, very bright. We can't actually see any part of the inside of the sun. But in order to study what is beneath the photosphere, scientists use vibrations of the sun. So use vibrations to see the convection of gases within the sun. And the vibrations resonate sort of like sound waves. So we're actually able to measure and observe the different layers of the sun, the different layers of the inside of the sun that have different thicknesses, different densities, and different chemical compositions. We're also able to use Doppler shifts to observe changes that we see in the sun's surface. So we see on the photosphere, on the surface of the sun, we can see where there's upward motion versus downward motion. And we can see where that is due to the vibrations that are traveling through the sun's interior. So we see the upward versus downward motion. When I say upward, I mean from towards the center of the sun outwards. So it's moving up on the surface of the sun, which means it is moving towards the earth. So material moving upwards within the sun is moving towards the earth. Material that is sinking or moving down away from the earth, it's going to be moving towards the center of the sun. So that will be red. So we can use this red versus blue of the Doppler shift to see how things are changing on the surface of the sun. So the other thing we can notice about the surface of the sun are called sunspots. So sunspots are spots on the sun's surface that are a little bit cooler than the rest of the photosphere. So sunspots are generally about 42,000 Kelvin, whereas the photosphere itself is about 6,000 Kelvin. So they appear very dark compared to the photosphere, but they're actually still incredibly bright. They're brighter than our full moon. They just aren't as bright as the photosphere itself. So next to the photosphere, they appear very dark. So sunspots last multiple weeks. They move, they shift, and the motion of the sunspots is due to the rotation of the sun, the fact that the sun is rotating. The average size of a sunspot is about 2 times the size of the Earth. So they look small on the surface of the sun, but they're huge. They're bigger for the most part than the surface of the Earth is. So if we look at the number of sunspots with time, here we have time increasing towards today. And here we have the number of sunspots. So you'll notice there's a very clear pattern. That here we have many, many sunspots on the sun, and then we have decreasing amount of sunspots, and then it increases again and decreases again, increases again, decreases again. So the number of sunspots on the surface of the sun has about an 11-year cycle. So in 11 years, we have a maximum number of sunspots, a minimum number of sunspots. And it's not only the number of sunspots on the sun that change, but it's also the location of the sunspots. So they first appear at higher latitudes, so closer to the poles, not quite at the poles of the sun, more like in the 30 degrees north and south-ish is where they will first appear. And then over time, they move closer and closer to the equator. So here is what we call the butterfly graph of sunspots because it looks like butterflies. We're looking at latitude. So here we have 0 degrees, which would be the equator of the sun, the North Pole and the South Pole. And here we have with time. So if we take this butterfly, for example, the sunspots start appearing close to 30 degrees north and 30 degrees south. Then as time goes on, the sunspots appear closer and closer to the equator until that 11-year cycle comes around again. They all start to fade out at the equator, and then they start again. So this we call the butterfly diagram. So the first sunspots appear at the higher latitudes, And as time goes on, they appear closer and closer to the equator, then it starts over as a cycle. And again, it's about an 11-year cycle. So in addition to sunspots, we have what we call active regions on the surface of the sun. So this is where we have disturbances in the chromosphere and the corona, so in those upper layers of the atmosphere. So this is generally where we have very, very powerful magnetic fields, or areas of the magnetic field that are very, very powerful, up to 10,000 times stronger than elsewhere. And we usually find these active regions where we have, or when we have, a peak in the sunspot cycle. So where we have the most sunspots, where we have the most disturbed magnetic field, is where we have these active regions. So the active regions are generally very, very bright in the short wavelength, so in X-ray and UV radiation, and they'll release really intense bursts of energy. So these active regions are generally what create solar storms and solar flares. So that would be when there's a blast from one of these active regions, where you have really high energy or short wavelength radiation blasting outwards from these very active regions. So the sun is not a solid. It does not rotate like a solid. It experiences what we call differential rotation. What this means is that the sun does not rotate at the same speed, at the same rate, all over the surface of the sphere. The equator actually rotates much faster than the poles. So it takes about 25 days for something at the equator to circle around a full circle. But at the pole, it's going to take about 35 days. So this is a phenomena occurring both on the surface and in the interior of the sun. So it's not just the surface, it's also the gases in the interior of the sun. It's not rotating at the same speed. So what does this mean? What does this look like? If we take these dots north to south on the sun and look at day 1, if we then look at day 5 days later, the dot at the equator is going to have moved much further than the dot at the pole. So it's going to take about 30 days for this dot at the pole to rotate around, or closer to the pole, to rotate back around to its starting position. But it's only going to take about 25 days for this dot at the equator to rotate around. So this can get a little messy. The sun's magnetic field is very, very intense, and it will create loops through the photosphere. So there's turbulence within the sun, which causes flickering of this magnetic field, flickering of these magnetic loops. And remember that the atmosphere of the sun is very, very low density, so it's sort of easy for the magnetic field to shift around and move around. Now, the motion of this magnetic field, the fact that the magnetic field is moving, heats up the atmosphere. So this motion of these magnetic field lines, the motion of these magnetic loops in the photosphere, is heating up the atmosphere. So what happens is the magnetic field, instead of being a nice bar magnet where we have the north at the north and the south at the south, it gets really tangled up because everything at the equator is moving much faster than at the poles. So if we start with this nice north-south orientation, the equator is going to rotate around much faster. It's actually going to pull the magnetic line so it looks something a little bit more like this. And then as it keeps going, we're going to pull the magnetic lines even further, to the point where we're almost bending the magnetic lines in half, where we have a south and a north quite close to each other. So the magnetic field gets so messy, it gets to the point where it's not strong in north or south anywhere because it's such a mess. Then all of a sudden, it's like there's no north and no south because it's too messy. So the whole magnetic field will just reorganize itself into something very, very simple, like this north-south again. This takes about 11 years. So it takes about 11 years for the magnetic field to get messy enough that there's almost no positive and negative, and it will totally reorient itself. Then the tangling just starts again because it's still experiencing that differential rotation. So you'll notice 11 years is the same cycle as the sunspot cycle. So where we have the messier magnetic field is where we're going to have more sunspots on the surface of the Earth. Sunspots generally on the surface of the sun. Sunspots generally will always occur in pairs. So there's always a north and there's always a south in a sunspot. And we have magnetic field lines coming out of the north and into the south. So the magnetic field works sort of like a bar magnet between these north and south ends of the sunspot. So we have the north, it's attracted to the south. The magnetic field is going to flow out of the north end into the south end of these sunspots. So the more sunspots we have, the more of these magnetic loops we're going to have, the messier the magnetic field will be. The closer the south might be to another sunspot's north, to the point where they aren't strong enough to differentiate each other. They'll all disappear, we will have no sunspots, and the 11-year cycle will start over. So here is an example of the sunspot. So we have the entire magnetic field of the sun. So we have the North Pole flowing to the South Pole. We also have these magnetic field lines in between, or on the surface of the sun, rising up into the atmosphere of the sun, using those sunspots, the sunspot pairs. They're always in pairs. So solar activity is always magnetic. So solar weather, solar storms, so any solar activity is always magnetic. It has to do with the magnetic field. And it is constantly changing. The magnetic field of the sun is always changing. And where we have this solar activity, for example, this is called a prominence. Generally what's happening is we have ionized gases getting trapped in the magnetic field. So ionized or excited gases will get stuck in this magnetic field of the prominence. So this is called a prominence. It is an arch of these trapped gases. So trapped in that magnetic arch, we can actually see the magnetic arch because it's picking up these gases and moving it through this prominence. So the prominence they're very, very tall. They usually reach up into the corona, just the lower corona, but they're huge. So this, for scale, is the size of our Earth. So here's us, the Earth, and here's just one prominence on the surface of the sun. So we can also see a prominence instead of looking from the side, because this is not the view we normally have of the sun. When we see the sun's surface, we call them filaments. So filaments are prominences that we see from above. So they will be less warm than the surface, and they will look black, look like sort of black lines. But we know that these black lines, they're filaments. They're actually just the prominences. It's the same thing. We're just seeing them from above. So seeing them on the surface of the Earth instead of viewing them on the side like this. So we're still seeing those ionized gases rising up into the corona. We know that they are then looping back down, back onto the surface of the sun. So solar flares occur in an active region. So remember, active regions are generally near the edges of the granules, near the sunspots, where we have positives and negatives meeting. So when a positive area and a negative area of the magnetic field actually meet, that's where we have what is called a reconnection event, or they cancel each other out. So if the positive and a negative, or the north and the south of two sunspots meet, they're going to reconnect and cancel each other out. What happens when this happens, we call it a reconnection event, is energy is going to be released. Very short wave, high energy radiation. So usually it's X-ray or UV radiation that explodes out of these reconnection events. So it only takes minutes, this reconnection event. It's very, very quick. There will be a big explosion, and the release of magnetic energy, the release of shortwave energy takes just a few minutes and sort of slows down and is completely done in about an hour. So this is a very short process. But this is explosion, the particles that are exploded from what we call solar flares can actually be carried all the way out of the atmosphere by the sun's solar wind. So remember, the solar wind is that extension of the corona, the fact that some of the magnetic field is pointing outwards. So the particles from these explosions can be carried all the way throughout our solar system in hours or days, and they can actually reach Earth. So what happens is the solar wind is carrying these high energy particles. If they reach Earth, they can, the high energy particles will actually enter our atmosphere through our magnetic field and create a current within our atmosphere. So the current will flow in at the poles, and it's going to excite atoms in our atmosphere. So the solar wind is carrying these high energy particles released from the solar flare. Those particles enter our atmosphere through the poles at the north and south ends of our magnetic field. Those high energy particles now create a current within our atmosphere and start exciting different atoms in our atmosphere. So what happens when an atom is excited? We have photons being emitted. So as that atom gets excited from this current, its electrons are going to jump up in orbit. They will then jump back down, releasing a photon, releasing light in some specific color depending on which gas is being excited, which atom. So what does this look like from the surface of the Earth? This is the aurora, or the northern lights or the southern lights, depending on which hemisphere you're in. So the excitement of the gases in our atmosphere because of this solar flare is what causes the phenomena we know as the aurora. So the different colors that we see in the aurora depend on the wavelength that's being emitted, which depends on which atom is being excited. So if you see red is you're generally going to see higher up in the atmosphere, so they'll be further from the surface of the Earth. That is oxygen that's being excited. So when oxygen is excited, it emits a photon at about 630 nanometers, which is in the red. So if you see red, it's a little more rare. You're looking at excited oxygen. Now, the most common color is green of the aurora. So most pictures and videos, the only aurora I've ever seen, both times have been green. And that is when nitrogen collides with oxygen. So nitrogen and oxygen, excited and colliding in our atmosphere, emits a photon at about 557 nanometers, which is in the green. So something to note is nitrogen and oxygen are the most abundant gases in our atmosphere. So there's so much nitrogen and oxygen available in our atmosphere that when we have an aurora, we generally see this green, because the most abundant things in our atmosphere will be excited the most. We generally see a green aurora. Now, if you see a blue aurora, you're in luck. This is the most rare. This is excited nitrogen on its own without the oxygen. So excited nitrogen is generally emitting at about 428 nanometers. So this is going to be really the highest level of solar activity, is going to create a blue aurora. If you see blue, you know there's a lot going on. That is some high energy solar flare coming into our magnetic field. And this will generally occur lower in the sky or lower in our atmosphere. Here's a GIF showing, this is sped up. I should note that this GIF and the previous one are sped up in time. It does flicker. You do see motion, but it doesn't move this quickly. This aurora here, you're seeing the green and the purplish pink there. Very sped up in time. So here I have a link to a really great video about the sun. It's called Sun 101 from National Geographic. I'm not going to play it for you, but it is a really great resource. I would check out that video if you're interested, and maybe as you're studying. It has some really great graphics, and it's really helpful in describing the layering of the sun and how the sun itself works.